Hello everybody. This is the last video for the section about separable differential equations, and we will go through one example. So the example is u prime of x is equal to cosecant of u times cosine of x over 2, and we have an initial condition of u of pi is equal to pi over 2. So this will be kind of similar to what we've done in example 4, but now we're dealing with trigonometric functions. Okay, the first step is exactly the same as before. We need to separate our equation. So let's rewrite du dx for u prime. Okay, and here we get cosecant of u, so you can think about it as 1 over sine of u times cosine of x over 2. Okay, so if we multiply everything by sine of u, we get sine u du on the left, and then multiply everything by dx, we get cosine of x over 2 dx. And again, we're going to check that everything on the left is in terms of one variable, u. On the right, we have x. We can integrate each side. Okay, so this is nothing new. We have done problems similar to this. Okay, let's see. We have sine of u and then cosine of x over 2. So these are straightforward antiderivatives. So the first one is negative cosine of u is equal to what? What do we get here? We get 2 sine of x over 2 plus c. Okay, so again, this is what we call implicit general solution, right? We have a constant c, but now we're going to use our initial condition to figure what that c is. Okay, that's what we're going to compute. So negative cosine, okay, u of pi is pi over 2, so pi over 2 goes here, is equal to 2 sine, and x is equal to pi, so pi over 2 plus c. Okay, negative cosine of pi over 2, that's 0. Sine of pi over 2, that's 1. So from here, we conclude that c is equal to negative 2. Okay, so our solution looks like what? Negative cosine of u is equal to 2 sine of x over 2 minus 2. Okay, so let's go ahead and graph and see what the graph of this curve looks like. Okay, and then we'll decide which part we're going to accept as our solution. So I already did the graph for this, and you'll see that you're going to get this infinitely many of this circular or elliptical objects, right? Okay, so and this makes sense because cosine is a periodic function, so we have this repetition. Okay, but that's not going to be the entire solution for our initial differential equation. So we go back to our original equation and see, do we have any restrictions that we need to keep in mind here? Cosecant of u. Okay, so cosecant of u is undefined. Undefined for infinitely many points, right? Okay, so it's undefined for those values where sine is equal to 0. So this would be 0, pi, 2 pi, and so forth. And also negative pi, negative 2 pi. But we're interested in particular, we're interested in 0. So whenever u is equal to 0, we have an issue. We have discontinuity, okay? So this derivative is not defined. Okay, so we have to take care of this. We're going to plug in u is equal to 0, okay, into star, which is our solution over here. So what's going to happen? Negative cosine of 0 is equal to 2 sine of x over 2 minus 2. And we need to solve for x. So this is a simple trig equation that we should have been able to do since taking pre-calculus, right? So negative cosine of 0, that's negative 1. 2 sine of x over 2, negative 2. So let's solve this. Negative 1 plus 2, that's 1. And let's divide everything by 2. We're going to get this equation here. Okay, so sine of x over 2 is 1/2, which means x over 2 is equal to what? So for which angles is the value of sine equal to 1/2? So one of them is pi over 6, and another one is 5 pi over 6. But this is x over 2. We need to solve for x. So once we multiply by 2, we're going to get x is equal to pi over 3 and 5 pi over 3. Okay? So we found these values of x for which we have discontinuity of the derivative, right? Okay, so we're going to restrict our x to be between pi over 3 and 5 pi over 3. Okay, so now if I go back to my graph here, on the second line I actually have the same function, but now restricted to only those values. Okay, and you'll see what's gonna happen. I'm just gonna have all of these circles right here, right? Okay, and they're not exactly circles. So I have these parts right here. So now which one of these do I pick? I pick the one that satisfies the initial condition, which was u of pi over 2 is equal to pi. So I highlight my point over here, and we get this branch, this upper part of this elliptical figure that crosses the x-axis. That is our graphical solution, okay, to the differential equation that was originally posted. So you can make a picture of what your solution actually looks like. Okay, let's go ahead and go back. Let's see, so what do we have here? So this is our initial condition. So we have this figure that kind of goes through what, 1 and a little bit more than 5. Okay, so just roughly we're going to sketch it like this. Okay, so these points, let's see, where is our point? Yeah, it's right in the middle. Okay, so that sounds good. Okay, so this is your pi over 2 pi. Is that right? Let me check. U of pi is pi over 2, so this should be backwards. It should be the other way around. Okay, so x is pi, u is pi over 2. All right, so here's another example of an equation that is, the integration part is simple, right? So we can integrate sine of u easily, and same for cosine of x over 2. But what's difficult, or can be difficult, is picking the right part of this curve that actually corresponds to the solution of this differential equation. Okay, so we have to go back and say, do we have any points of discontinuity? And yes, in this case, cosecant is the one that brings discontinuity. Cosine is defined for everything, right? So we go here and say, all right, well, if we do have u is equal to 0, what are the points that we need to exclude? So the points that we actually exclude, and let me highlight them in red, and these right here. Okay, these are the points that we need to exclude from the domain. Okay, all right.